Take everyone outer space. Okay, so Lucia's here. And so thank you all for doing the craft. And don't forget to take, oh, I think we have Parker has made a rocket and that looks awesome. Great job, Parker. I love it. I really like the square windows here. Maybe you're gonna put somebody in there. We'll look forward to seeing that. Okay, so yeah, once you're done with your rockets, take a picture and you can add it to the Padlet. But I'm gonna stop sharing and I'm gonna turn it over to Lucia and she will tell us all about space. So Lucia, take it away.
Great, thank you so much. All right, so I know that you've been doing an entire planetary themed night and we'll keep with that theme. But specifically, I'm going to start to focus on Mars. So a little bit about me. My name is Lucia Bellino. I graduated from Rutgers University in May of 2021, where I got my bachelor's degree in geology. And I just started my PhD in geosciences this fall at the University of Texas at Austin. And I'm really interested in using geochemistry and mineralogy and planetary science to investigate the climate of early Mars. And we'll talk a lot about the research that I do and about that climate of young Mars really soon. But before we get to Mars, we can start at the very beginning at the Big Bang. So you might have heard about the Big Bang before. And what it really is about 14 billion years ago, the Big Bang was an explosion where we had nothing and then there was everything that we know. And so that was the formation of the universe. And it's still expanding today. And so you might be like, how can we possibly know what happened 14 billion years ago? And there are three main pieces of evidence. I think that this one is the hardest to understand. It's called the Doppler effect, and it was discovered by a guy named Edwin Hubble. So if you've heard about the Hubble telescope before, that's the person that it's named after. And so he discovered something called the redshift using something called the Doppler effect. And the Doppler effect is that as you have something moving, the frequency is changing. So you might have heard like an ambulance or a train or a police car go by you, and you hear the noise that it's making from the siren change as it goes closer and further away from you. And the reason that's happening is because the frequency of those waves that you're hearing is changing as the car moves. And so the same thing kind of happens as galaxies move in our universe. And so they move as they get further away, they have longer wavelengths. And so there's a red shift, which means it shifts to longer wavelengths, to red wavelengths that are longer than the blue wavelengths. And so the only thing that's important to understand about this graph is that it means as you get further and further away, the velocity of galaxies that are further away from us are getting faster, which means that our universe is actually expanding. And so that's the first line, but I think that's the hardest to understand. Another piece of evidence for the Big Bang Theory is that there's this cosmic microwave background energy. And so you would think that if you had the Big Bang, you'd have this like huge explosion of energy, and there should be like some remnant energy still today. And so if there had not been any remnant energy, if you went into space and you took the temperature, it should be 0 degrees Kelvin. But the actual average temperature of the universe, and not just like of the Earth, but of the entire universe, which is everything that exists, is 2.7 degrees Kelvin. And so that's still super duper cold, but it exists and it's not 0 degrees, it's 2.7 Kelvin. And so some of this energy comes out, if you've ever seen TV static before, about 1% of the static on a TV signal is actually cosmic microwave background from the Big Bang. And so if you're watching your TV and you get a little bit of static on it, you're actually getting to experience like a little piece of evidence of the Big Bang. And the last major piece of the Big Bang, last major piece of evidence for the Big Bang Theory is that because this would have happened so fast, you've had this explosion of energy, you'd only be able to form the lightest elements. And so if you're familiar at all with the periodic table, you might know that hydrogen and helium are the lightest elements there. And so those are the main two elements that would be produced during the Big Bang. And so when scientists look at the concentrations of elements that were formed in the universe and that are present in the universe, hydrogen and helium are the most abundant elements, they're the ones that are most common. And that lines up with what we would have expected to see for the Big Bang. So now that we know how our universe existed, and that was 14 billion years ago, now we can kind of get into our solar system. And so after the Big Bang Theory, there was just like this gigantic cloud of interstellar dust. So just a bunch of pieces of these like elements that I just talked about how the Big Bang made, just kind of floating around like little pieces of like space dust. But around 4.6 billion years ago, so still a really long time ago, we ended up having something happen in around us that would have caused like a supernova explosion that would have caused a little cloud to form. So within the bigger cloud, a smaller cloud to form. And all the mass in the cloud would have started to accumulate in the center. So you would have had more and more mass going to the middle of this cloud. And if you've ever thought about like an ice skater, when they are spinning and spinning and they bend down and they kind of get smaller and they concentrate all of their mass in the center of something, they are able to spin faster and faster and faster. And that's kind of what starts to happen with this cloud, is that you have all of this stuff going to the center and going globbing around in the middle. And this disk starts to flatten out and it starts to spin faster and faster and faster. And eventually what happens is that it gets so heavy in the center here that the middle actually collapses in on itself and creates the sun. And so that sun took they took 99.8% of all of the stuff that existed in this cloud went into the sun. And so what was left of this, there's like 0.2% that was left over afterwards, ended up actually making all of the rest of the planets in our solar system. And so you end up having the planets form from the other pieces of dust surrounding the sun, where they just kind of have little pieces of dust that start to glob together, and then they get bigger and bigger, and eventually you have the point where you have like you have bodies that are like kilometers in size that are crashing into each other, making larger and larger bodies. And so this explains why we have our solar system, where if you know that you have rocky bodies closer to the sun, planets like Earth that are rocky, and then you have planets that are the gas giants that are really far away from the sun, they form because closer to the sun, it would be really hard to have water exist because it would be so hot and other like gases. But further out, you'd be able to have more of those kinds of elements. So we have like the rocky bodies, the rocky planets near the sun, and further away, we have the gas giants. And so here's our solar system. You might know what our solar system looks like, but just as a reminder, you have the sun, and then you have Mercury, Venus, Earth, where we are, Mars, and then Jupiter, Saturn, Uranus, Neptune. And so when I was talking about the 4 rocky bodies, those are the Mercury, Venus, Earth, and Mars. And then the big gas giants are Jupiter, Saturn, Uranus, and Neptune. And so now we're going to really start concentrating in on Mars for the rest of the presentation. I thought that it might be helpful if you don't have a lot of context for Mars to go over some things about Mars versus Earth. So Mars is actually a lot smaller than Earth. It's only about half of the size of Earth. And you know that we have 1 moon surrounding the Earth, right? But on Mars, there are actually 2 moons, and their names are Phobos and Deimos. And so just a little piece of like trivia is that Mars is the Roman god equivalent of the Greek god Ares. And so Ares' 2 sons in Greek mythology are named Phobos and Deimos, and they're the gods of fear and panic. So those are where the names for the 2 moons of Mars come from. And the Mars is nicknamed the red planet because it has like this reddish color to it, if you see this picture here of Mars. And Mars is a super cool planet that has a lot of exciting features that are really different than what we see on Earth. So for example, you might have heard of Mount Everest before. It's like the tallest mountain on Earth. And that's here, it's 5.5 miles high. And even though we often think of Mount Everest being the tallest mountain on Earth, Mauna Kea is actually partially underwater, which is why we don't think of it as being the tallest mountain on Earth. But that actually comes in at 6.3 miles, which is already so tall. But Mars has the largest volcano in the solar system, which is called Olympus Mons, and it's actually 14 miles high. So it's more than double as high as Mount Everest. It's gigantic. You can see to scale here how much larger it is than Mount Everest and Mauna Kea. And if you had a picture from space, here's Olympus Mons. You can see this volcano, how big it is coming off of Mars's surface. And here's a picture with Arizona, the state of Arizona, like to scale on top of Olympus Mons. And you can see that this volcano is basically as large as the entire state of Arizona. Mars has lots of other features that are kind of unlike anything that we've seen on Earth before. Here's another example called chaotic terrain. And I just think it's a really interesting and exciting, it's so interesting and exciting to see terrain and features that look so different than what we see on Earth. And the last feature I want to show you is this gigantic canyon called Valles Marineris. So here it is on Mars' surface. It's almost like a gigantic Grand Canyon, but you know, the Grand Canyon's already gigantic on Earth, but on Mars, this is the United States to scale, and the Grand Canyon would span the entire United States, or not the Grand Canyon, Valles Marineris would span the entire United States. That's how big it is. where it would be able to be the same length as like the entire United States, which is crazy. But something else that makes Mars really, really exciting is that a long time ago, 4 billion years ago, Mars would have had water, liquid water on its surface. And so a lot of times we only think of Earth having liquid water on its surface. And Mars doesn't have liquid water on its surface today, but there's a lot of evidence to support the theory that liquid water existed on Mars about 4 billion years ago. So, for example, here's a picture of one of the rocks on Mars that has it's called a conglomerate, but it would be formed from processes that had water carrying bigger rocks. You can see that these like pebbles that get put inside this larger rock. And then we also have a lot of features that we can see on Mars that look really similar to what we see on Earth. So in D here's what like a delta looks like. So it's obviously dried up on Mars now because it would have been water there 4 billion years ago. But you can see how, I'll show you in a second too, how it looks really similar to the features that we see on Earth of things like deltas, which are where you have a lot of like rivers and channels branching out. And then you also can see just like individual valleys and channels and the stream beds for those as well. And again, they're all dried out on Mars now, but you can see that they look really similar to what you might imagine if they were dried out on Earth, what they would look like. And you even have crater lakes where like if you would have had a crater, it could have had water. And then you have like rivers and channels that come out of that lake. And we also, we'll talk about this in a second a bit more too, but you also would have, we've also been able to detect minerals that have water in their structure using a special kind of camera that can take pictures of Mars surface, which I'll talk about soon as well. And here's when I was saying that you could see like a delta on Earth versus the delta on Mars. Here's what delta on Earth looks like. You can see that it's like, you know, blue is where all the water is and it's very green because there's lots of vegetation. But on Mars, you can see that the structure still looks really similar where the shapes that you see and the channels look really similar to what we see on Earth. And if you've heard of the Perseverance rover that's on Mars, it actually traveled to a delta location on Mars where we think that 4 billion years ago, there would have been liquid water. So we have all this evidence that there was liquid water on Mars' surface a long time ago, which is really exciting. But the really big question becomes, how could liquid water have existed on Mars' surface? Because 4 billion years ago, the sun wouldn't have been as bright as it is today. It wouldn't have been as luminous. And Mars is further away from the sun than Earth is. And so it would have been really hard for Mars to get enough radiation, enough sunlight just from the sun to be able to be warm enough to support liquid water. And so scientists came up with two different theories for how you could have liquid water existing on Mars' surface. The first theory was that you'd have greenhouse gases in Mars' atmosphere, like how we have greenhouse gases in Earth's atmosphere. If you think about, you've heard of like global warming and climate change and those greenhouse gases making the atmosphere, like making the Earth hotter. The same thing could have happened on Mars when we could have had things like volcanic explosions release gases like hydrogen gas or sulfur dioxide, which are kind of rare gases that would have been like able to keep heat on Mars's surface. The other theory, though, is that Mars could have been covered in ice sheets. And instead of having liquid water visible on the surface like how it is in the other model here, in this model, you'd have ice sheets, and then you would have had some kind of heat coming from the inside of Mars and kind of the bottom layer of the ice sheet melting to produce liquid water underneath of the ice sheet. And so my research was kind of hoping to be able to investigate this further, if it would be possible to have minerals that would have formed if you would have had this ice covering and then lots of heat and liquid water on Mars 4 billion years ago. And so I was specifically looking in this one area called the Iridania region. And basically what it is a bunch of these like interconnected basins, so like craters and stuff like that, all connected together to basically make this one gigantic area where there could have been a lake. And so, for example, if you see here how you have areas that are higher elevation and like the red and the yellow, and areas of lower elevation that are like the blue and the purple, this outline in black shows you where the Iridania Basin would have been, where all this water would have been, where there's lower elevation. So it's lower, so the water can fill in that area. And so you might think, how is it possible that we could know that this area might have had water in it 4 billion years ago, or that it would have been covered by ice on top of it? But there are certain ways we can look at the shapes of the geology in the region that tell us that ice might have been on top of it by comparing it to similar features that we see on Earth. and also the presence of certain elements or minerals that seem similar to what we see on Earth in environments that have like ice-covered lakes and things like that. And here's a picture of what the Eridania region looked like from space. Again, I think it's super cool. It looks really different from what I'm used to seeing on Earth. And you might also think, how is it important if we have this little basin on Mars? It doesn't look that big, right? But actually, it would have held more water on Mars than all of the rest of the lakes on Mars combined. And it would have been 3 times the largest landlocked sea on Earth, the Caspian Sea, would have all been in this Eridania Sea. So here's the Mediterranean Sea, which you might be more familiar with. It's still much smaller than the Mediterranean Sea, but for example, it's almost 10 times the size of all the water that's contained in all of the Great Lakes on Earth. And so we're really excited about this region because it would have had so much water there. And we think if there could have been ice on top of it, there should have been some kind of heat as well coming from the inside of Mars. And so if we would have had water and heat, we would have expected certain minerals to form. And a scientist named Mikulski was able to find a lot of different minerals that have water in their chemical structures in this area. And there's one in particular called serpentine, which he found in this region over here. And serpentine is really cool because not only does it require water and heat to be able to form, it also produces something called hydrogen gas as it's formed, like the process of forming this mineral. And so there are entire ecosystems on Earth that are underwater that are just bacteria that are able to survive off of the products of serpentinization. So this mineral is formed, it releases hydrogen gas, and the bacteria can basically like eat the hydrogen gas and consume it for energy. And so they don't need other food. They're able to just use that hydrogen gas. And so if we would have had serpentinization and serpentine forming on Mars in this region, it means we would have had heat, we would have had water, and we would have had hydrogen gas, which there are bacteria on Earth that can use that for food, which means we would have had all of the ingredients for life on Mars 4 billion years ago. And I'm not saying that life existed on Mars 4 billion years ago. I'm just saying that if we could find serpentine, it would mean that all of the ingredients would be there. But at this point, we were kind of thinking, okay, so even if you could find this mineral, how would it have been possible that enough heat would have been able to be produced from inside Mars that you could have a mineral that requires really high temperatures to form? But if you've heard about radioactive decay before, you might have heard about it in terms of like radioactive elements like uranium. And so there are other elements like potassium and thorium, and it's not the kind of like potassium that's in your bananas, it's a special version of potassium that are unstable, and in order to get more and more stable and to be able to exist to be able to exist stably, release energy along the way. And so when they release energy, they produce heat. And so it would have been enough heat that would have allowed temperatures that were high enough to create minerals like serpentine it would have been able to reach temperatures that were pretty high. And so you can see here in these graphs, the areas that are like orange yellow mean there are really high concentrations of these radioactive elements that decay and produce lots of heat. And these 4 triangles represent the 4 main basins in the Eridania region. And so all of the basins are in areas where there is really high concentration of radioactive elements, which basically is important because it means there would have been able to be a lot of heat produced in these regions so that serpentine could form and that liquid water would be warm enough for liquid water to exist. And so with all this information, I was hoping to be able to detect hydrothermal mineral alteration, which basically means that minerals got changed because of water and heat that were around throughout this Eridania basin, throughout this region, to be able to figure out how this region formed and if it really could have been a hydrothermal system, a system that had water and heat. So I used this data from a special instrument that orbits Mars called CRISM, which stands for the Compact Reconnaissance Imaging Spectrometer for Mars. Here it is here. And it basically is like a special camera that takes pictures of Mars' surface. And it orbits at 300 kilometers above Mars' surface. And so I'm going to show you pictures really soon. And they look like they're pretty tiny, but every single pixel in one of those images, every pixel is 18.4 meters wide. So actually, look at these pictures. We're looking at like miles and miles on Mars' surface. And so you might be like, how is it possible that we could take special pictures of Mars and be able to figure out what minerals were on Mars' surface? And so if you remember me talking a little bit about wavelengths at the beginning for the Doppler effect, we're kind of going to go back to that right now. So when you see things, we're able to see the visible spectrum of light. And so it ranges from purple to red. And so you might know you can see all the colors in the rainbow. And so everything on Earth or everything like in the universe absorbs certain colors and it reflects certain colors. And so, for example, a leaf really absorbs red and blue light. And so the main light that's affected is the green light. And so when we look at it, what we actually are seeing is the green light. And so this instrument is basically a special kind of camera where instead of looking in the visible light spectrum, which is what we can see and what cameras that like we have the camera on our phone, it would take pictures looking at the visible light spectrum that we can see. It basically takes pictures in other wavelengths. It takes pictures at 430 different wavelengths in the IR spectrum. So not in the visible light spectrum, but in the infrared ray spectrum. And so in order to do this, I have to download images from the internet, and they're NASA images. So if you ever wanted to download a CRISM image, you'd be able to as well. And I use special software to correct for Mars' atmosphere and to be able to do some other corrections so that I can actually look at it. And then I can start actually looking at the data in the areas that seem interesting to see if there are actually minerals that are hydrated and see if I could actually find serpentine that I had been talking about before. And so what I did was in this Iridania region, which is the same region we had talked about before, I looked at 350 images in the basin, and I was able to analyze all of these to see if I could find hydrated minerals. And I was able to find that about 70 of these 350 images contained hydrated mineralogy, and including about a third of them had some detections of serpentine in them. And so in case you were curious to see what these images kind of look like, here's the terrain that it looks like. I just think it's really interesting because it looks so different than what we see on Earth. And so though we've been talking before about how like leaves absorb certain wavelengths and they reflect other wavelengths, this kind of goes back to this where the minerals also absorb certain wavelengths and reflect other wavelengths. And so what I really wanted to see is which wavelengths they were absorbing. And so serpentine is able to absorb a wavelength at like 1.9 microns, another wavelength at about 2.315, and another wavelength at 2.5-ish microns. And so when I looked at these images, I was hoping to find that find areas that had these same absorption bands. That's what they're called when you see these kinds of like dips in the spectra. And so here, for example, are 2 lab samples of serpentine. So people on Earth were able to take samples of serpentine in a lab and find out what the spectra look like. And here's what mine looks like from Mars. You can see that these ones also have these absorption bands, and my sample has the same absorption bands at these areas that are important to say, yes, this could be serpentine. And this band right here is just the water band. So when you see an absorption band at 1.93 microns, you're able to say that means that the mineral has water in its structure. And so this one, for example, doesn't have that 2.51 microns band, so it's not serpentine, but it still has the 1.93 micron band, so it means it does have some water in its structure. And so this is really exciting because I was able to detect serpentine and other hydrated minerals throughout the Iridania region, which helps us support the theory that the Iridania region would have been a hydrothermal system, that it would have had heat and water that would have allowed conditions that make certain minerals form. And it's really exciting because the process of forming this mineral called serpentine produces hydrogen gas, which there are some bacteria on Earth that are able to use metabolically. So it means that we would have had water, heat, and something that bacteria on Earth, at least, are able to eat. So there would have basically been all of the ingredients for life on Mars 4 billion years ago. Thank you so much to Dr. Adamo and Julie and Ria for organizing this event and letting me participate. And thank you lots to my advisor, Dr. Oja, who helped me with all of this research and then also let me use a lot of his information from the Geology of Moons and Planets class that I took a couple years ago. All right, thank you.
Thanks, Lucia. That was really great. There are a lot of questions on the doc. I can send it to you if you need it.
I have it right here. Okay. So the first question was, are there meteorites from Mars? And the answer is yes. And there actually is even a small one of those at the Geology Museum. The next question was, do I have a favorite planet? And my favorite planet is Mars, just because I've done so much work on Mars. How did I get involved studying Mars? I started studying Mars because I took this geology of moons and planets class at Rutgers. And I thought that Mars was so interesting because before I took this class, I never even realized that there were other planets that ever had liquid water on them other than Earth. That was like purely an Earth thing. So I was so excited to find out that there could be implications for life existing on other planets. And I thought that Mars was just so exciting because it was so similar to Earth, and has these kinds of implications for life existing in other planets a long time ago. Do I want to live on Mars, or would I go to Mars? I don't know. I really like Earth, so I'm not sure I would leave Mars. But it would be really exciting if other people go to Mars and bring back samples so that I can look at those samples for Mars. How long did it take for the sun to form? It took like 50 billion years. So basically that big cloud of so basically this like big cloud of stuff sat for like 10 billion years before the sun started to form. And then once the process actually began of this, like all of the matter kind of like going glumping towards the center, it actually took like 50 billion years. So somebody asked, NASA recently deflected an asteroid through the DART mission. Can the debris from the deflection come back to Earth and contribute to the climate? That's a really interesting question. A lot of times our atmosphere is able to burn up most of the like meteorites and asteroids that come through the atmosphere. And so they could probably get burned up in our atmosphere before they actually made it to the surface if they're small enough. But I'm not sure actually about that one. I'll have to look into that one more. And I'm not sure when those burn up if they contribute to the climate a lot. A supernova is just the death of a star. So it's like when a star explodes, it's called a supernova. Where did the gas and dust come from in the initial dust cloud? Could it be from past solar system? So that's a really good question. So at first when you had the Big Bang, you'd have this like giant cloud of dust and elements and gas, and that would have just been formed from the Big Bang. But it's true that there could be other solar systems, or mostly like other like supernova or other kinds of like weird stars. Like there's these things called like neutron stars that are really strange, that are able to form other elements. And those ones got incorporated into our planet and other planets in our solar system. Then they recently find water on Mars. I remember reading an article about finding water a couple of years ago. Was this liquid or ice? So there's ice at the poles of Mars. And I think that there was a paper that came out a while ago that they think that there could be water like in the subsurface of Mars, or like ice in the subsurface of Mars. But I think that's really debated. So I think that the only thing that we know right now is that there is still ice on the poles of Mars. Is lava on Mars similar to the lava on Earth? Is there any data on its makeup or physical characteristics? That's a really good question. I think that Mars is a lot smaller than Earth. And so on Earth, there's like really different elements in the mantle versus on the crust, because it had a lot more time to like separate out. So when you have a planet form, it's really hot, and then you'll have kind of like layers form based on how dense those elements or those minerals are. And so the Earth has like very different structure than Mars, because Mars had to cool off a lot faster just because it's much smaller. So you think about having like a bigger pot of water versus a smaller, cup of water. When they cool off, the smaller cup cools off much faster. And so is the lava on Mars similar to the lava on Earth? I think it's somewhat similar, but I think that they are different. And I think that they've been able to do a lot of, the scientists have been able to collect a lot of information on the data, or about like the makeup or the physical characteristics of the lava, based on things like the CRISM instrument that I showed you, and other data from other instruments that are also able to get chemical data. And we're also able to learn some stuff about like what Mars looks like based on meteorites, but I'm not sure how much that tells us about the lava. Is there a timeline of when water existed on Mars to carve out all of the rivers and lakes features that we see left over today? I think that most of it happened between 4.5 and 4 billion years ago. And we're able to tell a little bit based on, there was one picture in my slide that had like different, when you have it was called the Amazonian, Hesperian, and Noachian, we're able to kind of age and date the terrain. And so some of that helps us figure out when the liquid water existed on Mars. But I think that we're still pretty unsure of when exactly the liquid water stopped existing on Mars, because we're not really sure how it's possible liquid water could have existed on Mars in the first place. But I think around 4.5 to 4 billion years ago is the main time that liquid water existed on Mars. Does Mars have sedimentary rocks? It does. It has lots of sedimentary rocks on Mars. And so like that one like Perseverance rover that's there right now is looking at some of those sedimentary rocks. Is there any mission that will study and bring home rock samples to Earth? That's what they're in the process of doing right now. So I think that the Perseverance rover is the like first step in trying to bring rock samples home from Mars. But I think that's going to take us like 10 years or something crazy. So hopefully we'll have rock samples in the future from Mars, but I think it'll be a long time. For now, because we have meteorites that come from Mars, we're able to study at least those for now. And they have, can Earth become like Mars someday? I think that at this point, Earth is very different from Mars, but it could definitely become dried out and not have water anymore. A lot of it is dependent, I think, upon when the Earth finishes cooling off, because our magnetic field depends on the Earth still having some internal heat, and that magnetic field is really important for a lot of things on Earth. So part of why Mars is so different than Earth is because Mars doesn't have that magnetic field anymore. And so I guess it's possible, but I actually don't know fully what people predict that Earth will look like, billions of years in the future. Does Mars have Mars quakes? Yes, it does. I think that the mission recently died, but there was a mission called InSight that was on Mars that was able to measure the Mars quakes on the surface, or not on the surface, but was able to measure the Mars quakes on Mars. Does Mars have plate tectonics? No, Mars does not have plate tectonics. Earth has plate tectonics, but Mars does not. And often earthquakes on Mars are causes. So often plate tectonics on Earth is what causes earthquakes on Earth, but on Mars, the earthquakes are much smaller. And then how do I conduct my research? Do I do any experiments in the lab? So for the research that I showed you, all of it was just done on the computer. It was just with like data from this instrument. But now in my PhD, I'm hoping to do a lot more experiments where I could do, I could take samples that look kind of similar to like samples that we see on Mars, and then like from Earth, and then do experiments on them. So I don't really do experiments in the lab, but I'm hoping that I'll be able to do experiments in the lab soon. Mars is red because there's lots of iron. If you've ever seen rust before, Mars is red because it has lots of iron, which is iron causes that like reddish rust color. And so that's why Mars looks red. It has lots of that iron. Is Mars very hot? Mars is actually very cold. So it's actually much colder than the Earth is. And it's a very cold planet. Why are Uranus and Neptune considered to be twin planets? That's because their size and the composition of them, so what they're made of, and the way they rotate are really similar. And so because of all those similarities in them, they're sometimes called twin planets. Philip would also like to know if they have sent any probes to Mars's moons. And I'm not positive about that, but I don't think that we've sent any kind of instruments to actually look at, actually touch down on Mars's moons. Is there water on any other planet or the moon? So currently, our moon doesn't have any water on it, but scientists believe that the moon could have had water on it a long time ago, and that there are other moons within our solar system that would have had a lot of liquid underneath of the surface. And so, for example, Saturn has a moon called Enceladus that people think would have a lot of liquid water on it, and same with Jupiter's moon called Europa. And then both of those would have almost have more like salty oceans more than fresh water, and they'd be covered with these like ice sheets on top, kind of similar like how we've been talking about the Eridania region, if it would be covered with ice and then have water underneath. Similar, but with really thick ice sheets. These moons would have really thick ice sheets and then oceans underneath them. Did Mars ever have hydrothermal vents? And that's a lot of what my research looked at in that area. We think that it would have been a hydrothermal region that would have had a lot of hydrothermal alteration. And I think that it probably would have had hydrothermal vents like what we see on Earth. And then Philip wants to know, is there enough atmosphere on Mars for it to rain? It's a really good question. So today, definitely not. Today, there's not liquid water on Mars, and there's not enough. It has a really, really, really tiny atmosphere. But a long time ago, that's what scientists really ask themselves. Would Mars's atmosphere have been like thick enough for there to be rain on the surface? And so some scientists think that yes, there would have been. Other scientists think definitely not, that it would have just been like ice covered and that you wouldn't have had rain. You just have liquid water underneath the surface. All right, I think those are all of the questions.
Yeah, thank you. Thank you so much, Lucia. I think that was all the questions. There were so many of them. You did a great job and we learned so much. So thank you once again. And thank you to all of our viewers who tuned in today. And don't forget to mark your calendars for our next event, so our next event is actually, I believe, Julie, is it the next late night?
We have an Ask a Geologist coming up, but I have not advertised yet. I believe it's late October. I'll put it on the website shortly.
Okay, so look out for the announcement for our virtual Ask a Geologist. Or that will be, as Julie has said, she was going to put the information up for that. Beyond that, our next late night event will be November 2nd. That one is going to be an Egypt theme. So once again, thank you all, and thank you, Lucia. And I hope everyone has a great night.